Hello and welcome to Note Quiz number 13, which is regarding systems of equations and inequalities. So the idea behind systems is looking at multiple equations at the same time and trying to find solutions that make them all true at the same time. And with that, we have some different terminology to discuss as well. The first one is going to be consistent. If our system has a solution, we call the equation consistent, and if it doesn't, we call it inconsistent. The next term to discuss is called dependence versus independence. Dependent means that we have an infinite number of solutions. That could be something where two lines are on top of each other or two planes coincide. Or it could be where we have one solution and that's where it is independent. And that would be the crossing of two lines in that case. So let's now get into some examples. The first thing you want to do is determine if we have ordered pairs given to us, solutions of a system. And so the idea here, compared to before, is we have to make sure that all the equations are true. So let's first take a look at the first ordered pair, which is negative 2, comma 3. If we take negative 2, comma 3, and we substitute it into the first equation, we're going to have a negative 2 plus 2 times 2 times positive 3. And that does make 4, which checks in the first. For the second equation, that is y, which is 3. And a question mark, is that equal to negative 1/2 times the x, which is negative 2, plus 2. Well, negative 1/2 times 2 is going to be positive 1. And then plus 2 makes 3. So we get 3 equals 3. So that first ordered pair does check out. And so let's circle it with a yes. All right, now let's do the next one, and that is 4, comma 0. Once again, we substitute into both equations. So for the first equation, that is 4 plus 2 times 0, and that does make 4, so it checks in the first. For the second, we want to see if 0 is equal to negative 1/2 of 4 plus 2, and that does make negative 2 plus 2, so that checks out as well. So the ordered pair 4, comma 0 is also a yes. And then finally, we're going to check the ordered pair, which is 3, comma 2. Down here in the notes, it says 3, comma 1/2, but we're going to check 3, comma 2 since that's what's printed in our question. So for 3, comma 2, substituting in, we're going to have x, which is 3, plus 2 times the 2. You'll see quickly that that's going to make 7, and that is not equal to the 4 on the right-hand side. So not a solution. And what's nice about systems is if you have an ordered pair that doesn't work in one of the equations, it's automatically not going to be a solution for the whole system either, because you have to make all the equations true. So again, this one, the answer is no, it is not a solution. So again, to determine if an ordered pair is a solution, we substitute it into all the equations in the system and see if we get a true statement. All right, so now let's move on to actually solving different types of systems. And so the next thing we're going to see is what's called the graphing method. This method is probably the least used of all methods because it requires us to draw a very nice, accurate graph to get a solution. So when we graph our first line, we have choices. Let's use the slope-intercept method for the first one. So if I graph the first one, I'm going to solve for y. And that's going to be 2y is equal to positive 3x minus 9. Divide both sides by 2. And I get the line y equals 3/2 x minus 9/2. And so our y-intercept is negative 9/2, which is negative 4.5. So when I go down to plot this line, I'm going to start down there at negative 4.5. And have a slope of 3/2 means I'm going to go up 3 and right 2. So that's my second point. And then my next one's going to be up 3 and right 2. So it's going to be right there. So we just need to sketch a line passing through those 3 points and try to draw as accurately as possible since we're using the graph to answer the question. All right, so that's the first one. Again, we use slope-intercept for that. For the second equation, let's go through and use the x and y intercepts. So for the x-intercept, we set the y equal to 0. And when we do that, we're going to have negative 2x minus 3 times 0 equals negative 6. So negative 2x equals negative 6. Divided by negative 2, we have x equals 3. So that's the ordered pair 3, 0. And then we'll find the y-intercepts as well for the same line. We're going to set the x equal to 0. So that's negative 2 times 0 minus 3 times y is equal to negative 6. And we have negative 3y equals negative 6 divided by negative 3. And y is a positive 2. So that intercept is 0, 2. All right, so again, for our first one, we'll graph it in green. So we have 3, 0, which is right there. And then we have 0, 2, which is right there. So the second linear equation has this graph. So now we want to find the solution. And remember, the points on the graph of an equation make it true. So all of the points on the blue line give us the solutions for that equation. All the points on the green line give us the points for the second solution. So of course, where they intersect and cross, that's going to be the point that makes both of them true at the same time. And if we read that ordered pair off, it looks like the point 3, 0. So from the graph, we have 3, 0. And we already know 3, 0 lies on the green line because that's how we got the graph in the first place. If we substitute 3, 0 back into the original equation, you will see that we've got negative 3 times 3 plus 2 times 0. That does make a negative 9 equals negative 9. So that point does check. So our solution again is the ordered pair 3, 0. Because we have a solution, we say it's consistent. And because there's only one solution, it is independent. So that is how we find a solution from graphing lines. All right, so I'll move on to now an algebraic method. The algebraic method is called the substitution method. And what's really nice about these methods we talk about today, they are going to be very explanatory. Because if you're doing a substitution method, you'll probably find yourself substituting in the problem. So this requires a little bit of a strategy to go into the problem. So what you want to do is look at both of the algebraic equations and ask yourself which one has a variable that is very easy to isolate. And you'll notice that the top equation has an isolated x in front of a 4y. So I can easily solve for x in that equation. X is just equal to 14 minus 4y when I subtract 4y from both sides. Now what's key with substitution is you now take what you solved for and you substitute it into the other equation, which is really important. It's the other one. So we have now a original 2 times the x, which is 14 minus 4y, minus the 4y that's already there, is equal to negative 8. And you'll notice that we made things much easier because we now have one equation with one unknown. And that's the goal of the substitution method. And again, it's always important to make sure you substitute into the other equations. If you substitute it back into itself, you just get a true statement, which is useless. All right, so now let's go ahead and solve this equation very quickly. We multiply the 2 times the 14 and get 28. The 2 times the negative 4 is minus 8y, minus the 4y behind it equals negative 8. Combined like terms, that's 28 minus 12y is equal to negative 8. Subtract 28 from both sides. And I don't need to draw a bar there. And negative 8, take away 28 is going to give us negative 12y equals a negative 36. Divide both sides by negative 12. and you end up with y is equal to positive 3. Because we want a solution for a system, we also have to go back and get the x number. And you will notice when you're doing substitution, it's very nice because you already have a formula for x. So x is just going to be 14 minus 4 times the 3 we just found. So x is 14 minus 12, or just 2. So your solution is the ordered pair 2, 3. And again, because we got a solution, we call it consistent, and we got one solution, so it's independent. All right, so that's the substitution method. Again, in summary, you pick the equation that has the easiest variable to isolate. In this case, it was the first one for x. You then solve for that variable and substitute into the other equation, solve to get the one variable, and then go back to get the other. So again, that is how we use substitution to solve a system. The next method is called the elimination method, and you guessed it, we're going to be eliminating a variable. So the key here, again, is to try to make your life as easy as possible by trying to eliminate a variable with the least amount of work. And right now, if we were just to take these two equations, you'll notice that nothing cancels. The 3 and the 11 would make 14, and the 2 and the minus 8 would make a negative 6. Not helpful. So instead, what we want to do is multiply one or both of these equations by a number so that when you add them up, one of the variables cancels. And so for the first equation, you will notice that if I multiply by 4, I will get an 8y that matches the negative 8y. So that's what we're going to do. We're going to take our first equation and we're going to multiply by a 4. And you always make sure you do it on both sides of the equation. So multiplying by 4 will give us 12x plus 8y equals a negative 44. The other equation is staying the same. It's 11x minus 8y is equal to negative 25. We can now take those two equations and add them up. And in doing so, we get 23 times x. And again, the y's cancel. So if you want to, you can just kind of slash those out. And that equals up to, looks like negative 69. And then we divide both sides by 23. And we get x is equal to exactly negative 3. It actually goes in evenly. Now, the downside is once you use this method, you don't have a quick, easy formula to get the other variable. But you still want to pick the one that looks like it's less work. So I'm going to take the first equation, the 3x plus 2y equals negative 11. And I now take that x equals negative 3, and I substitute it in place of that x. So I've got 3 times negative 3 plus 2y equals negative 11. That's just negative 9 plus 2y equals negative 11. And then if I add 9 to both sides, I get 2y equals negative 2. Dividing by 2, I get y equals negative 1. So this solution is negative 3, negative 1. And once again, we are consistent and we are independent. And that is what's called the elimination method. Sometimes called the addition method because in the process you add the equations together. So for the next couple of problems, we're going to be combining these methods together and looking at the different possibilities for outcomes. So far everything's been one solution, which means consistent and independent. So for these next couple of equations, we're going to see where we're going to be using those other terms. So for the first one, you can solve it any which way you like. In either case, it's always important to make sure that you have your variables in the right order. So you'll notice the first equation, well, that's fine because that has the x first. So we have 3x minus 6y equals 4. For the second equation, you will notice that I need to bring the y over. So it's still a 6x over there, but now minus 12y equals 6. And for this equation here, it looks like elimination might be the least amount of work. So let's go through and divide and multiply both sides by a negative 2 in the first equation. So this one will get a negative 2. And the idea there is that it will change it to a positive 12y. The other equation is going to stay the same. So I'm going to have a negative 6 times x plus positive 12 times y equals negative 8. The other equation is still 6x minus 12y equals 6. And when I add these up, you will notice something very interesting happening. On the left side, everything cancels, and I get 0. On the right side, I'm stuck with a negative 2. And we know that 0 will never equal negative 2. That's a complete impossibility. So we have no solution for this equation. In other words, we'll never find a pair of numbers that make them both true at the same time. Because of that, we use the term inconsistent. There's no solution. And because they're actually going to be a different line, because they're not crossing, they are independent. All right, so now let's take a look at the next equation. You'll notice the next equation allows us to pick either method to solve. Let's go ahead and use substitution this time around just to kind of make a different variety of problem. So let's go through and take our second equation, and you will notice that I can go through and solve for y very easily. So I've got 20x equals 16 minus 4y. I can subtract the 16 from both sides. So I've got negative 4y is equal to 20x minus 16. I can divide both sides by negative 4. And that takes me to y is equal to negative 5x plus 4. Remember that negative 4 must divide into that negative 16. Remember now we take this and substitute into the other equation using substitution. So this equation is going to substitute up here in place of our y. So after we make that substitution, I'm running out of different colors here. I'll just use red, point down this way. We're going to have 2 originally there times the y, which is negative 5x plus 4. And that's still equal to 8 minus 10 times x. Multiplying this out, I'm going to end up with negative 10 times x plus 8 equals 8 minus 10x. I can then add 10x to both sides. I can then subtract 8 from both sides. And you end up with 0 equals 0, which is always true. What's different about this problem is the fact that because you get a true statement, you are now going to have an infinite number of solutions because it's true for all values of x and y that you plug in. So what you're going to do is you're going to go in and substitute and write down here that we now have a consistent solution or system because we found the one answer, but because we have an infinite number of solutions, we'll call it dependent. And what's a little different for this problem is the fact that we now have to describe the set of solutions. And instead of being just a single ordered pair like before, we now have a set. It's going to be the set of ordered pairs where the x number can be anything we want, and then the y number is always going to be negative 5 times x plus 4. And x is any, and I mean any, real number. And again, the idea is I can pick a value of x, substitute it into this formula, and get a y number, makes a solution. Pick another x, substitute it in, get another solution. For example, if x is 0, then y is 4. 0, 4 is a solution. If x is 1, Then -1 is the y number, and that's a solution. And again, I could list out ordered pairs of x and y's that make these equations true, this equation true forever. There's no limit. So that's the case where we have a dependent system and we have an infinite number. When it comes back to graphs, this means that the one line is completely on top of the other line, whereas the no solution is where the two lines are parallel and never cross. All right, so let's move on to a couple of different application problems. Our first problem is called a mixing problem because we're mixing solutions together. So again, problem one, or the first application, a mixing problem. So in problems like this, it is extremely important to make sure that you carefully define your variables, because once you do that, it makes the equations easier to write, and it also makes the system easier to solve and interpret at the end. All right, so we've got a pharmacist who's going to be mixing a 40% saline solution with a 12% saline solution to get 119 milliliters of a 32% solution. So we're basically mixing some liquids together to create a new liquid. And so what we're going to do first is define our variables. We're going to let x, again, you can pick any variable you want, but it's just traditional for x's and y's. X is going to be the number of milliliters of our 40% solution. And then the y number is going to be the number of milliliters of the weaker 12% solution. So now we have to write two equations for these two unknowns. And there's always one equation that's a little simpler to write because of the fact that it's usually containing the volume of something. And so in this case, since we want to have a total of 119 milliliters, that means that the x and the y must add up to make 119. And if you're thinking about this equation, it is milliliters plus more milliliters equals more milliliters. So you can kind of think of this as your volume equation, keeping track of how much liquid you have. And now the next equation is going to take into account the actual amount of saline or salt dissolved in each of these solutions. So the first one is a 40% saline solution. And to get 40% of something, you always convert to a decimal and multiply. So that's going to be 0.40 times x. So 0.40 times x is going to give us the amount of saline in our mixture. Just like for the 12%, you take a 0.12 times the amount of liquid you have, and that gives you how much saline is coming from the second solution. Now, since we're mixing them, we want to end up with a 32%, and it's 0.32 or 32% of the 119 milliliters. And this you can think of as your saline equation. And now we've written successfully two equations for our two unknowns. We can solve them. You can solve them any way you want to, but I think you'd agree that substitution looks easiest because it's so easy to get the x and y from the first equation. So we're going to take this equation and we're going to solve for the y number. So from that first equation, we know that x plus y equals 119. So y is equal to 119 minus x. We can now take this and substitute this into the other equation right there. So that makes 0.40x plus 0.12. There's a decimal there, make it a little darker. And that's going to be times the y, which we know is 119 minus x. And that equals the product of 32 and 119, which is 38.08. All right, we can now distribute. So we got 0.40x plus the product of 0.12 and 119, which is 14.28. Minus the 0.12x that we distribute equals 38.08. Combine those like terms together, we get 0.28x, and we move the 14.28 to the other side, we get 23.8. Dividing both sides by the 0.28 gives us x is exactly 85 milliliters. We can now go back to any of the equations above to get the y. I'm going to pick the easy one, which is the one that's in the green box. Again, we know that y is equal to 119 minus x. So y is 119 minus 86, which ends up being 34 milliliters. So remember, x represented the amount of the 40%. So we put 85 milliliters here. And again, that leaves the y to be the 34. And if you think about our solution, those two numbers do add up to make a 119, which is good. And you also notice that we're taking more of the stronger one to get that, because 32% is closer to 40%. So it makes sense that we would need a lot more of the 40% to get it to that level and less of the lower, weaker 12% stuff. So again, that's how we go ahead and solve a mixture problem. And you could go back and check both equations to make sure the solution does make sense. All right, so our next equation is a distance rate time problem. And that formula is D is equal to R times T, sometimes called the dirt formula, by the way. And so here, we're going to have a fishing boat that's traveling along the east coast of the U.S., encountering a current. It's going to be traveling 50 miles north with the current of 2, and this will be 2 hours of travel time. So again, we have a current and we're going with it, gives us a little push. And then we're going to have us traveling 39 miles south against the current, and it's going to take us 3 hours. So the idea here is to find the speed of the current and the boat. And so the first thing you want to do is pick variables to represent each one of them. So once again, like before, we're going to let x equal the speed of the boat, and that's in still water. So assuming there was no current at all. And then we're going to let y equal the speed of the current. All right, so the next thing we need to do is look at the two different directions that we're traveling. So for the first one, we're going to be going north. And when you are on the north trip, you're going a total of 50 miles. So that's our distance. And that's equal to the rate that we're actually traveling at times the amount of time that we're traveling. Well, when you're going with the current, it's giving you a boost. So the actual speed you have is the speed of the boat plus the current. And then you multiply that by the amount of time you're traveling, which is 2. And so we got the north, and then we've got our south. So for the south, you will notice that we are going a shorter distance, 39 miles. And then when you're having the boat go against the current, it slows you down. So it's x minus y. And that trip is 3 hours long. So our system is the first equation and a second equation. Let's just write them down right here. So 50 is equal to x plus y times 2, and 39 is equal to x minus y times 3. So you can solve this by using elimination or substitution, but you will notice that one thing you can do in these problems is actually simplify first before you go solving the equation. If you take the first equation and divide it by 2, which is the same thing as multiplying by a half, and you take the second equation and you multiply by a third, which is dividing it by 3, you will nicely downsize all of your coefficients. The first equation becomes 25, and that was supposed to be a y there, by the way. So let's change that back to a y. That's x plus y there. All right. So that's 25, and then when I divide both sides by the 2, that just be x plus y only. And then for the other equation, the second one, when I divide 39 by 3, I get 13, and then dividing the right side by 3 cancels it, and I get x minus y. So now we have a really easy system that we could solve by just adding the equations together. If I add them up, I'm going to get 38 is equal to 2x's because the y cancels, and then dividing both sides by 2, I get x is equal to 19. And remember, that was the speed of the boat in still water, so that's not just 19, it is 19 miles per hour. And then to get the current, I can use any of these equations that I want. To get the y, I'm going to pick the easiest one of them all, which is this one right here. If I know that 25 must equal to the x number, which is 19 plus the y, I can just subtract 19 from both sides, and I get 6 miles per hour for my current. So we get answers which makes sense because remember, a boat's gotta be faster than the current if you're gonna make any progress traveling on the water. And you'll notice that it's always a sizable difference. So the boat's going 19 and the current is going 6. You also notice we don't have any crazy numbers with negatives or anything else because we have speeds of everything. So that's a distance, rate, time application. Now let's move on to systems that are bigger than 2 equations. When systems have 2 equations with 2 variables, they're sometimes called 2 by 2, just because that's the dimensions of the system. When you get to an equation that has 3 variables, and it's got to have 3 equations with it, we call this a 3 by 3 system. So if you hear me referring to 3 by 3 system, that's what we're talking about. 3 by 3 just means there's 3 variables and there's 3 equations. So again, this is a 3 by 3 system. And in note quiz number 14 coming up next week, we'll see a lot of different ways to solve 3 by 3 systems, especially using what are called matrices. For this first time here, we're not using matrices. We're just going to solve the equation as it's written. And you have really 2 choices at this point. Either use substitution or elimination. Most people opt probably for elimination here, but I'm going to use substitution because I want to show you that as well. So let's go through, and again, we're going to pick the easiest equation with the easiest variable to solve for. And this one's kind of a tie. You notice that the first equation has an easy x to solve for. The second one has an easy y. I'm going to just solve for the top equation in terms of x. So here, when I move them over, the x will be by itself on the left. The negative 9 is already on the right. And then I have a minus 3y plus a 5z. And now this is going to be substituted into the other 2 equations. So this is going to be in the x in the second equation and in the x in the third equation. So I'm going to kind of use different colors here to show this, but the 2 is originally there in the second equation. The x again is being swapped out with negative 9 minus 3y plus 5z. The plus single y was already there, minus a 15z was already there, and so was the negative 8. And then for the second equation, it leads off with a negative 2 times the x. The x is still negative 9 minus 3y plus 5z. And then this equation has a minus 2y next, a plus 5z, and then finally a 1. What you'll notice here is we've taken our 3 by 3 system and knocked it down to a 2 by 2 system, making it smaller and easier to solve. So the next step in solving this is going to be to distribute and combine like terms and make it as simple as possible. So the first equation is negative 18 minus 6 times y plus 10 times z plus the y already there minus the 15z already there equals negative 8. Down here we have a negative 18. Actually, it's a positive 18 because there's two negatives there. So positive 18 plus 6y minus the 10 times the z minus 2y already there plus the 5z already there equals 1. All right, combining like terms. Let's see here. Combining the y's, I'm going to first have a negative 5y. If I combine my z's, I have minus 5 times z. And then if I add 18 to both sides, I'm going to get a 10. And then down here for the second one, 6y minus 2y is 4y. I've got minus 10z plus 5z makes minus 5z. And then I'm going to have 1 minus 18, and that makes negative 17. All right, so we will now go ahead and use substitution to solve this 2 by 2 system. Let's take the first equation, and we will just substitute and solve for y. So let's go through it. First step is to add 5z to both sides. So minus 5y equals 10 plus 5z. Divide both sides by negative 5. And I get a positive y is equal to minus 2 minus z. That's why I crossed my z's, because they look similar. We're now going to take that and we substitute it into the other equation. So that goes into that y right there. So we've got the 4 already there times the negative 2 minus z minus 5z equals 10. Oh, nope, supposed to be 17 there. Be careful. Again, distribute and combine like terms. Negative 8 minus 4z minus 5z equals negative 17. Combining like terms, negative 9z minus 8 equals negative 17. Add the 8 to both sides. Gives us negative 9z equals negative 9. And finally, divide both sides by negative 9. And we get z is positive 1. So now that we have z equals 1, we can now back substitute to get our value of y out of this. I know that y is equal to negative 2 minus the z number, which was 1. So y is negative 3. I can now take that and back up to the beginning and have that value of x and that value of y come from that value of y and z. So here I've got x, I've got a negative 9, I've got minus 3 times the y, which is negative 3, plus 5 times the z, which was 1. So x is negative 9 plus 9 plus 5. That makes x equal to 5. So we now found the values for all 3 of our variables. The solution is written as an ordered triple, which means it's going to have the x first, then it's going to have the y number, and then finally the z number. And what we found here is 3 numbers that will make all 3 equations true at the same time. And that's what it means to be a solution for a 3 by 3 linear system. All right, so next up, let's now do an application of this. All right, so for this next problem here, we want to find the equation for the parabola that passes through three given points that are not in the same line. So it's going to be a true parabola and not a default smushed one. So let's go through here and notice that if you're going to fit a parabola, you need to find the values of a, b, and c in the quadratic equation. So what we're going to do here is take each of our ordered pairs and put them into this equation. So starting off with 0, 7, substituting that in. The y I know is 7, the a is unknown, and the x is 0 squared, plus b times that same 0 for x, plus c. That simplifies down to nothing more than c equals 7, which is very nice. For the next equation, we've got 223. So y equals, so 23 equals a times the x squared, so it's 2 squared, plus b times x, so b times 2, plus c. That gives us 4 times a plus 2 times b plus 1c equals 23. And then finally for -5, 37, same story. The y is 37. That's equal to a times -5 squared plus b times -5 plus c. And that gives us 25 times a minus 5 times b plus c equals 37. So our system of equations is, and you can write it in any order you want, it's 4a plus 2b plus c equals 23, and 25a minus 5b plus that same c equals 37. And the third equation is a trivial c equals 7. So again, this could be solved a variety of ways, but I think you could agree with me that substitution is probably the way to go, since we already have c pre-solved for. If c is equal to 7, then we can just plug that in for c in the other two equations. So that means 4 times a plus 2 times b plus now 7 equals 23, and 25a minus 5b plus, again, c, which is 7, equals 37. If we then subtract 7 from both sides, we get a 4a plus 2b equals 23, take away 7, which is 16. And we've got a 25a minus 5b is equal to just plain 30, because 37 take away 7 is 30. All right, so from here, we can now solve different ways. One thing you will notice again is you can downsize the equations by multiplying to cancel out the larger numbers. In other words, for the top equation, I can multiply the whole thing by a half. And for the second equation, I can multiply the whole thing by 1/5, which really is the same thing as dividing the first by 2 and the second by 5. All right, so now when I do that division, I'm going to have just a single 2a plus b is equal to 8, and 5a minus b is equal to 6. I can then just add these up and get 7a is equal to 14. Divide both sides by 7, and I get a equals 2. And I now have my a number and my c number. I just need my b number. I can go back to any of these that I want. I'm going to pick this one because it's definitely the friendliest. So I know that 2 times a, which is 2, plus my unknown b is equal to 8. So that's just 4 plus b equals 8. So b is just 4. So now remember the goal here, it was to actually find a quadratic equation for the final answer. So my solution is going to be an equation. It is y is equal to a, which is 2, x squared, plus b times x, which is 4 times x plus c, which we know is 7 from before. So if you go in and graph this parabola, you will notice it passes through the 3 points that we were given at the beginning of the problem. And you could either put that into a graphing calculator or Desmos, or you could just pass the points to the equation and verify that they make it true as well. So that's the easiest way to fit a parabola through a line, is to go through and set up a 3x3 system. All right, so next up, let's take a look at what are called nonlinear systems. And nonlinear systems are going to be systems where we no longer have lines. We're going to be looking at curves like parabolas, circles, and things of that nature. All right, so for our first problem here, they want us to use the graphing method to find a solution, and then they want us to go through and verify algebraically by solving it using a different method. So we're going to graph both of these, and the first equation is ready to be graphed because we know how to graph y equals x squared minus 4. You can either treat it like a quadratic function graphing problem from the previous module test, where you find the vertex and the intercepts, or you can use transformations and just remember that this is the original x squared graph vertically shifted down 4 units. So my parabola is going to have a vertex now at -4, and it should be pretty obvious that if I plug in a 2, I get a 0, or if I plug in a -2, I get a 0. So that right there is going to be the x-intercepts for my parabola. But because I'm graphing this and I want to be very, very careful, I want more points because I don't want to have a sloppy graph. So let's take x equals 3. If x is equal to 3, 3 squared is 9, minus 4 is 5. So this parabola passes through 3, 5. And I can't go any further because 4 squared is 16, take away 4 is 12, and that's off the graph. But by symmetry, I know that if I have points that are 3 units over this way, I must also have points that are 3 units back that way. Remember, we have even symmetry for parabolas. So now when I graph this thing, I'm going to have a nice, neat parabola that passes through the 5 points that we found. All right, now the second equation here, it's a linear equation, but because we have the parabola, we still call the system nonlinear. So back to this equation here, if we take it and we solve for y, we've got subtracting 3x from both sides. So I've got a negative y is equal to negative 3x plus 4, dividing by negative 1. I get y is equal to positive 3x minus 4. So this equation here has a y-intercept of negative 4, which again, we'll graph this actually, and we'll graph it in red. So it passes through 0, negative 4. And then the next point, we go up 3 and right 1. So up 3 units and right 1 brings us here. And then up 3 and right 1 takes us here. And it takes us there. And this is where my parabola got a little sloppy there at the end, because it does not cross another time. It needs to be a little steeper. So let's kind of curve that back up like so, and back up like so. So now when I draw my line through my 4 points I have, you will notice that the line crosses the parabola down at the intercept, which we said before. So that's our 0, negative 4 number. And then the other one is going to be here at the ordered pair 3, 5. And at most, a line and a parabola will cross at 2 places. So from the graph, we'll say we have 2 ordered pairs. We have, again, 0, negative 4 being a solution, and what looks like the point 3, 5 to be a solution. All right, so now let's go ahead and solve algebraically. So again, just copying the system down, I've got y is equal to x squared minus 4, and then the other one is 3x minus y. is equal to 4. All right, so when you're starting to solve equations that are going to be nonlinear, substitution works most of the time, and you'll notice here that this one's ready for substitution because I have my y already solved for. So I'll substitute into here, and my equation is 3x, and then minus, and then the y I'm putting in is x squared minus 4, and that equals the number 4. And I should make that consistent, put that in black. All right, so again, that equals 4. All right, simplifying this down, I've got 3x minus x squared plus 4, be very careful there, equals 4. And then I can subtract 4 from both sides. I'm left with 3x minus x squared equals 0, which is a quadratic equation, so I can try factoring it or use completing the square, the quadratic formula. Factoring, it's actually pretty easy. Taking out an x, I'm left with 3 minus x. So here, either the first factor, x is equal to 0, or 3 minus x is equal to 0, so x is equal to 3. So when x is equal to 0, I now need to find the corresponding y number. And the corresponding y number comes from what we solved for already. We've got y is equal to x squared minus 4. So y is going to be 0 squared minus 4. So y is negative 4. So that makes the ordered pair 0, negative 4. Now when x is equal to 3, we know that y is equal to x squared minus 4. So y is going to be 3 squared minus 4. So y is 9 minus 4, which is just 5. Makes the ordered pair 3, 5, which looked like the point we saw on the graph. So our solution is now going to be 2 ordered pairs. It's going to be 0, negative 4, and 3, 5. And some people like putting these in set notation if you need to, but the idea here is these 2 ordered pairs are a solution. And again, they correspond to where the graphs crossed at those 2 points. All right, so let's move on to another example of a nonlinear system. You notice this one has squares in it. And what you want to notice here is I don't want to do substitution unless I'm clever about it. So technically you could solve for x squared or y squared here and have squares to solve for and work with. But you will notice here that I can also use elimination for this equation because of the fact that I've got a very similar structure. So here we're going to use elimination, again, more for variety than anything else. So the top equation, I'll notice that if I had an 8 in front of the y squared, it will cancel with the negative 8y squared in the other equation. So I'm going to multiply the entire top equation by a positive 8 and then put the result right behind it. So that's going to make a 48x squared plus 8y squared. And if I multiply 15 and 8 together, I get 120. Again, the other equation is just staying the same. 5x squared minus 8y squared equals negative 67. If I now take these and add them up, you will notice that those squares for the y cancel, and I'm left with just plain 53. X squared is equal to, actually 53. Dividing both sides by 53, I get x squared is equal to 1. Now, once again, we have an equation where we have a lot of different ways to solve it in the class. Easiest way to do this one probably is square root method. So I get x is equal to plus or minus the square root of 1, and of course the square root of 1 is 1. All right, so now we can take either one of these equations and solve for the y. Again, if you look at the top equation, that's the nicest one because the y squared is already without the coefficient. So I can just replace x squared remember this original equation here, equals 1. So if I do that, I'm going to have 6 times 1 plus y squared is 15. So 6 plus y squared is 15. So y squared is 9. Just like before, I square root it. And I end up with y equals plus or minus 3. So now when you translate this, you have to think about these are all possible solutions, which are points. So there's a total of 4 different possibilities. You can have the x being 1 and the y being positive 3. But you could also have the x being a positive 1 and the y being a negative 3. You could also have x being negative 1 with y being positive 3. And then finally, you could have both of them negative. If you go back and check out these 4 ordered pairs, they will make both of those equations true at the same time. So this nonlinear system has 4 solutions. And if you were to go to a graphing calculator or Desmos, you'd see these curves cross at 4 places. So quite a few solutions there. All right, now let's move on to our very last problem. And our last problem is looking at a quick example of solving a system of inequalities. And inequalities, again, are very different because by nature, they already have an infinite number of solutions. So we have to find a better way to find answers instead of just picking pairs and seeing which ones work. So what we want to do is graph both of these lines, and they're going to be treated like barriers. So let's first start off with the top equation. We're going to take this top equation, and we're going to do it with the color blue. So it's already solved for y, which makes it really easy to graph. It has a y-intercept of negative 3. So it crosses through down here. And then it has a slope of a half, which means we're rising up 1 and going right 2. So we connect those dots. And now when you're dealing with inequalities, you have to check to see the greater thans or less than symbols. Because this is a greater than or equal to, we use a solid line. If it was strictly greater, it would be a dashed line. But because we have the equals bar, we're going to use a solid line to graph that boundary. The next thing we do is we test out an ordered pair to see if it's true or false. And you should always try to use the ordered pair 0, 0 when you get the chance because it's the easiest one to work with. So we're taking the origin 0, 0, and we're substituting it into the first equation. It says that 0 is greater than or equal to 1/2 of 0 minus 3, which simplifies down to 0 greater than or equal to negative 3. And that is true because 0 is bigger than any negative number. So what you do is you shade the side that had the 0, 0 on it. So this right here is a set of all ordered pairs that makes the first inequality a true statement. We now repeat the process for the second one. And so for the second one, we're going to graph that one in green. Again, it's already solved for y, which makes it nice. It's got a y-intercept of negative 2. And it's got a slope of 1. So which means we rise 1 and we run over 1. So the green line is going to be the other barrier. You will notice it's also a equals bar under the less than. So we're going to shade this with a solid line because of that. And just like before, we take out a test number. So in green, we will test out, and because again, that green line does not pass through 0, 0, it's fair game for testing it. So again, in the top one, let's just write that real quick. We tested out 0, 0. For this one, we're going to use the same 0, 0 origin. So that is 0 less than or equal to 0 minus 2. So is 0 less than or equal to minus 2. And that is false because negatives are all smaller than 0. So this is a false statement. So we shade the other side of the graph, which is the stuff under the green line. So these are all the ordered pairs that make the second inequality true. Now remember, we're actually solving a system here. So the system is going to be the set of all the ordered pairs that make both of them true. And hopefully it's kind of obvious that the region that we want is what's double shaded, because if it's shaded by both, then it makes both true. So I'm going to use the color red for that, but that is this triangular wedge that is right there. So everything inside of this triangular wedge is the solution of our system. And what that means, again, in theory, is I can take any ordered pair in this red region and it will make both of those inequalities true at the same time. And if I take something in the blue region, it makes one true. If I take something in the strictly green region, it makes the other one true. So only the red region makes both true at the same time. And again, we really can't write this out in a set notation or anything else because there's an infinite number of points with multiple ways to describe them. So we just use a picture to represent the solution for our systems of inequalities. All right, so that takes us to the end of note quiz number 13. Again, note quiz 14 will be all about matrices coming up in our last section for the class.